Good afternoon. Welcome to another episode, and today we will be talking about infinite sets. Alright, in order to explain this, let's begin with something a little different, the concept of equality. So, the question that we're trying to answer here is that what does it mean for two things to be equal, right? And we're trying to generalize this. So let's begin. So let's begin with something really obvious. So for example, A is equal to B. Now, what do we actually mean when we say that two things are equal? Well, one thing is pretty fairly obvious, that if something is equal to it, something must be equal to itself. So A is indeed equal to A. The next thing is that if A is equal to B, then B is equal to A. That's the second property. The third property is that if we have A equal to B and B equal to C, then we can conclude that A is also equal to C, right? And with these three properties, we can now generalize the notion of what it means for two things to be equal. Right, so to recap, when we say that two things are equal, we actually are describing those two things by the properties that they have. So the first property is that of reflexivity, which means that A is equal to A. The second property is called symmetry, which means that if A is equal to B, then in fact B is also equal to A. And the third property is called the transitive property, which means that if A is equal to B and B is equal to C, then we can conclude that A is in fact equal to C. And with that in mind, we can now generalize the idea of what it means for two sets to be equivalent. Okay, so now let's answer a question, which is when do we say that two sets are equal? And by equal, I mean they have equal. Alright, so by equal I mean that they have equal cardinality. And you may wonder, what do I mean by cardinality? Well, it's just a fancy mathematical way of saying that two sets have the same number of elements. Alright, so let's look at a basic example. So for example, let's look at the set A, B, C, and let's compare it with the set 1, 2, 3. And if I wanted to ask you, how do you know precisely that these two sets are equivalent? Well, one really basic way of answering that question is that I can match each element to another element. So for example, I can match A to 3, I can match B to 2, and I can match C to 1. And similarly, I can match 1 to C, 2 to B, and 3 to A. And with this in mind, we can actually describe what it means for two things to be equal. Alright, so mathematically speaking, two sets A and B are said to have equal cardinality if there exists a bijective map between the two. So, by a bijective map, what I mean is that we can match the elements onto each other. So, we can match 1 to A, 2 to B, 3 to C, and similarly we can match A to 1, B to 2, and C to 3. That is what I mean that our map is bijective. So now I'd like to explain how bijections are in fact equivalence relations. So we need, in order to prove that bijections are equivalence relations, we need to show that the three properties which I described earlier are satisfied. So let's go case by case. So the first property is that of reflexivity. So if I have a map from A to A, then clearly A is related to itself, because quite trivially we can show that we can just map each element onto itself, right? So we have reflexivity. Now let's move to the second property, which is that of symmetry. So let's say I have a map from A to B. Then the inverse map, which is from B to A, is also a bijection. So in other words, if I can map 1 to A, 2 to B, 3 to C, then I can also reverse that process. So I can map A to 1, B to 2, C to 3, and that's what I mean by the inverse map. And from that we can see that we have the property of symmetry, which is satisfied. And now we will move to the third property, which is that of transitivity. So let's say we have two functions. One maps A to B and the other maps B to C. So if I were to compose these two functions, so I were to take the map C, which maps A to C, then I can conclude that that is also a bijection. So a way to show this to you would be like, for example, I have a map which maps, for example, 1 to A and then A to Y. Then if I were to do that in one go, for example, I was to map 1 to Y, 2 to X, and 3 to Z, then I would also arrive at another bijection. So we have the property of transitivity, which is also satisfied. So to recap, we have now shown that bijections are in fact equivalence relations, and with that in mind, we can now extend this idea to infinite sets. Alright, so let's take the idea of bijections and now extend it to infinite sets. So let's take a particular infinite set which we all know, the natural numbers. So we have 0, 1, 2, 3, 4 and so on. And now let's take the integers. So by the integers I mean the natural numbers and the negatives. So we have 1, minus 1, 2, minus 2, 3, minus 3 and so on. And if I were to ask you a simple question, which set is bigger, right? You would obviously say that, well, this set is much bigger than this set, and the reason for that is quite obvious, that it contains all of these numbers. So it contains 1, 2, 3, 4, but it also includes the negative numbers, minus 1, minus 2, minus 3, and so on and so forth. And it would seem that these two sets are, that this set is bigger than this set, but mathematically we can actually show that these sets are in fact equal, and we will use the properties of bijections to actually show this. So let me provide a description of this. So let's take the even natural numbers first. So we have 0. 0 is an even natural number. We have 0, 2, 4, 6, 8, right? And now let's look at the negative integers. So we have minus 1, minus 2, minus 3, minus 4, and minus 5. And what I can now do is take each even natural number and map it onto a negative integer. So I map 0 onto minus 1, 2 onto minus 2, 4 onto minus 3, and so on and so forth. And now I can do the same thing but with the odd numbers. So let me use, so let's now look at the odd numbers. So we have 1, 3, 5, and 7. And now let's map these onto the positive integers. So we have 1, 2, 3, 4. And we can map 1 onto 1, 3 onto 2, 5 onto 3, 7 onto 4. And we can just continue with this process of mapping the even numbers onto the negative integers and the odd numbers onto the positive integers, right? And by doing this, we have in fact found a bijective function, because this is 1 to 1 and on to, so we can invert this as well, like I said before. Interestingly enough, this is the smallest form of infinity that we know, and we call it countable infinity, and represented by the Hebrew symbol aleph, and we call the cardinality of the counting numbers. So anything which can be counted is called a countable infinity, and we represent it by the Hebrew alphabet aleph, and we call the cardinality of the natural numbers equal to aleph null. And interestingly, and aleph in Urdu, if you know about that. So, and interestingly enough, this is the smallest form of infinity that we know, and there are actually more forms of infinity, and if you're interested in finding out about them, do leave a comment below. Thanks for watching.